Parto in italiano e poi passeremo in inglese, visto che abbiamo dei colleghi dall'estero collegati. So I will start just a few words in English, in Italian, then we will switch to English for the seminar due to colleagues from abroad. So I'm Nicola Mondillo. I'm professor at the Department of Earth Sciences at University of Naples, and I'm here to introduce Francesco Putzolu, my colleague, my former student. So just few words to introduce Francesco. He did his early career, started his early career in Naples, doing the bachelor degree and the master degree at University of Naples on bauxites and nickel laterites. He also did in Naples the PhD in on the nickel laterites. Then he moved to UK for the postdoc. He participated in two relevant projects on lithium specifically, and he had the honor, also the responsibility, to study one of the most iconic new discoveries in Europe, so the Jada deposit. And I can say that he did a very great, fantastic work that was published in Economic Geology last year. The publication is open access. And the seminar today is given because he got a prize from the Italian Geological Society, and specifically the section on mineral deposits. So, as the best publication of last year. So, Francesco will give us a full view of the Jadar deposit, its origin, geology, and so on. So, please, Francesco, and thank you for being here.
So thank you very much for the introduction. And before getting started, I want to acknowledge again the ore deposit section of the Geological Society of Italy for giving me this award. So with this presentation today, we're gonna go through a geological journey to understand the characteristics of the Jada volcano-sedimentary lithium deposit, which is a pretty unique mineralization style observed only in this locality. And again, I want to acknowledge all the research group involved in this work. And this piece of research has been put together within the Lithium for Future Technology project funded by NERC. So this project lasted between 2021 and 2024, and we had several people working on different aspects of lithium mineralization in different crustal settings. So we had people working on continental brites, volcano sedimentary deposits, and magmatic hydrothermal systems. When it comes to myself, I was involved in the study of volcano sedimentary deposits and granite pegmatite systems. So, as Nicola mentioned, we had several papers hitting literature on this topic, and most of them are really accessible. And when it comes to the other deposit, so we are dealing with an unconventional style of mineralization. So the other deposit can be grouped within the volcano-sedimentary lithium deposit class. We are basically dealing with shallow lithium mineralization hosted within continental lake systems. So this kind of system are characterized by a high degree of hydrological closure because we want to minimize the lithium outflow because lithium is a really mobile element. On top of that, another key feature is the spatial and temporal association with highly fractionated magmatic province because silicic magmatism is going to be our source of lithium and associated elements. Now, lithium can be transported from the igneous to the volcano-sedimentary environments in different ways. One way is, for example, eruption of volcanic glass-rich lithologies. Another way could be exsolution of high-temperature fluids coming from the underplating granitic magma. Either way, as soon as lithium-enriched volcanic igneous material is transported into the volcanosedimentary environment, we have a series of diagenetic processes breaking down igneous material to form secondary assemblages made of lithium clays, lithium borosilicates, phosphates, and so on. Now, based on mineralogy, we have proposed an updated classification scheme to describe volcanosedimentary deposits. So in most of cases, we're going to be dealing with the clay-type lithium mineralization, where lithium is associated with smectites like hectorite, a magnesium lithium smectite, or with lithium illite. When it comes to the Jada deposit, we're dealing with a pretty unique mineralogy because lithium is associated with jadarite, a hydrous lithium and boron borosilicate. And this kind of mineralogy has been only observed in the Jada locality so far. Now, Jada and jadarite have been discovered in 2004 during a mineral exploration program conducted by Rio to discover borate resources. And jadarite, as a new mineral species, has been defined by several scientists from the Natural History Museum in London in 2006. Now, the jadarite discovery back then had a pretty significant media coverage because it turned out that the jadarite stoichiometry is pretty close to the chemical composition of kryptonite observed, described in several Superman comics. So you can imagine that Superman fans got pretty excited about it, but they discovered that jadarite is not green, it's pretty dull and white, and obviously it doesn't glow. Despite Superman comics were not satisfied, jadarite is a pretty unique mineral when it comes to mineralogical studies and to economic potential. Why? Because if we look at the jadarite stoichiometry, we can see that it can accommodate around 7% lithium oxide, and these are lithium oxide concentrations pretty close to those observed in spodumene, the high-grade lithium pyroxene observed in LCT pegmatites. But on top of that, jadarite can also accommodate pretty high boron oxide concentration, up to 50%. So basically, jadarite brings together the best of both commodities, okay? So pretty unique mineralogy, and we all know that when it comes to mineral deposits, mineralogy can play a pretty important role to define the overall economic potential of a mineralization. So to get into the details of this kind of idea, this is a lithium grade tonnage compilation of the major lithium deposits globally, subdivided by deposit type. So at the bottom, in the low grade end of this plot, we have continental brines. At the top, in the high grade end of this projection, we have high grade LCT pegmatites. What about volcanosedimentary deposits? They sit, in most cases, right in the middle. So these are intermediate grade systems. Why is that? Because in most cases, lithium is going to be enriched into smectite. And smectite doesn't have the capability to accommodate as much lithium as spodumene. But jadarite and Jada are an exception to it, because jadarite can accommodate up to 7% lithium oxide, and as a consequence, the average lithium grade is displaced into the field defined by LCT pegmatites. So having an idea about mineralogy is pretty important, because mineralogy controls grade, which in turn controls economic potential. So when we first started looking at Jada, we were dealing with a strange beast, because it's an unconventional and poorly studied and new mineralization style. So we had to tackle some pretty fundamental geological questions. Question number one: which are the overall characteristics of the iodide trap. So orthasis and lithogeochemical variation. What is the association degree between the iodide and other species forming alongside it? And eventually, what is the consequence on the iodide formation conditions? Also, what is the interplay between low temperature and high temperature fluids, and what is the environment of formation? And also, what is the iodide stability window, and what is the consequence when it comes to the potential to preserve the iodide in the geological record? And what happens if the iodide gets dissolved? Do we have any metals remobilization? And finally, what kind of relationship exists with magmatism? Because magmatism is important because we want to have a source of lithium and associated metals. So in this presentation, we're going to try and find some answers to these points. But before doing that, let's have a look at the general geology. So we are in Eastern Europe, in the Balkan region. And the recent geology of this part of Europe is basically controlled and shaped by the collisional cinematics between the African and European plate. So during this collision, at some point, we have the development of a suture zone, here represented by this red geological feature. And within this suture zone, stretching from Western Balkans towards Western Anatolia, we have at least 20 volcano-sedimentary basins, either mineralized or with potential for mineralization. And all of these basins are somehow associated with highly fractionated igneous rocks, granites, and extrusive counterparts. So magmatism is important. And when it comes to magmatism, we have two stages of magmatism in this area. We have an Oligocene stage during which we form igneous-type granites, which comes to the lithium fertility. But during the latest stages of continental collision, we have the gravitational collapse of the orogenic belt favored by back-arc extension. So we push the astenospheric mantle towards the top. We have the upwelling of hot astenospheric material, leading to thermal anomalies within the crust. So we start melting metasediments and forming sedimentary type granites with potential to source lithium in the volcano-sedimentary environment. Okay? Now, if we focus on the other area, we can see that the other basin is pretty close to the Mount Sur complex, which is one of those granites recording these two stages of magmatism, okay? And extension and hyperextension is really important to control the local geology of this area, because we can see that hyperextension led to the uplift of the Mount Sur granitoids and also led to the formation of these extensional basins, among which the other basin. Now, if we look at the other basin, we have a Miocene volcano-sedimentary sequence lying on top of pre-Miocene metamorphic basement rocks. When it comes to the Miocene sequence, hosting the mineralization, it is very diverse in terms of lithology. We have lacustrine shales enriched in dolomite and containing epigenetic and strata-bound iodide nodules, here, these white nodules. But we can also observe iodide in association with altered intrabasinal tuffs, as you can see in panels B and C. And in addition to iodide, we also have borates into the system, forming these late genetic breccias, disrupting the sedimentary layering, okay? Now, let's get into some data. And the first question would be understanding how we can use lithogeochemistry to have an idea about the lithium and boron mineralogical residency. So what we did here is comparing the lithium and boron geochemistry with the ideal composition of iodide represented by this red dashed line. So the overall idea is that if we have a good agreement between the tendencies of the data with the iodide stoichiometric line, the chemical composition can be explained by the presence of iodide. But as soon as we see an offset of the data from the ideal composition of iodide, this means that lithium and boron are associated with other mineral species. And we can see that most of data actually follows the iodide stoichiometric line. And this is no surprise because iodide is present into the system. But at the same time, we can see a subset of data showing a boron excess over lithium, and this can be explained by acknowledging that we have lithium-free borates into the system. On the other hand, we see a subset of data showing a lithium excess, and this is due to the presence of lithium smectite into the system. Now, if we look at the overall feature of the lithium and boron domain, we're dealing with a lacustrine-Ørsted mineralization with our nice white iodide nodules associated with dolomitrite in a lacustrine shale. And if we look at the modal mineralogy, the main feature to observe is that the iodide amounts are nicely correlated with major amounts of sodium zeolites and of dolomite. Now, if we look at the petrography of these species, we can see that the iodide nodules sits within a fine-grained matrix made of igneous minerals, just like muscovite, detrital bitite, and so on. And iodide is posted within a primary dolomite generation. But the most important feature to observe is that iodide is most of times associated with sodium zeolites like analcime and natrolite. So if we want to put forward a preliminary and simplified pathway, we could imagine this kind of processes. So we start putting volcanic material into the basin, then we have the precipitation of primary dolomite followed by iodide and zeolitization, okay? If we look at intrabasinal depths, these are mineralized as well, because we can see that we have both borate and iodide forming spherulite, and in general, spherulite are a proxy of very specific processes like volcanic glass devitrification. When it comes to modal mineralogy, the most important feature here is the amount of K-feldspar. You can see that sometimes K-feldspar can be as high as 90% volumes. So this kind of K-feldspar, these kind of amounts are kind of odd for a primary igneous assemblage. In fact, if we look at the petrography, we can see that K-feldspar are not primary. These form the secondary fine-grained ground mass. So these are secondary species. And within K-feldspar, we have lithium smectite nodules and iodide and other borate.
Tutto bene, tu?
Just a bit. Let me tell this guy to switch off his microphone.
Cioè?
Right. So far, we have mostly dealt with a series of mineralizing processes taking place shortly after sedimentation, so early diagenesis. But locally within the system, we also have lithologies showing late genetic process. So this is the case for brecciated lithologies. In brecciated lithologies, we have local just a bit.
Ho capito. Perché tu sei andato, uscire sempre dal metro? No, perché sei un po' lontano. No, allora, Merignano e San Donato non mi sembrano così distanti.
Scusate, potete spegnere i microfoni?
Un po', però se almeno 2 giorni a settimana riesco a essere su San Donato vuol dire impiegarci un po' meno e casomai andare anche in metro.
Just a bit, sorry about that.
Però in ogni caso non faccio la tangenziale ovest.
Ok.
Ah, yes. Ok. Aspetta, uscire questo schermo. No, scusate, fammi uscire.
Okay, sorry about that. We had some technical issues. So, brecciated rocks, late genetic process. In these rocks, what we see is that jadarite doesn't form nice nodules. Instead, we have this fine-grained, strange-looking jadarite, which is really tricky to spot. In fact, local geologists used to call this jadarite generation ghost jadarite. And in this case, if we see the modal mineralogy, we can see that jadarite is associated with significant amount of albite and chlorite. Okay, and if we look at the petrography, we have some kind of positive feedback of this kind of idea, because we can see in pink there that jadarite is clearly late genetic and is a pervasive replacement of the rock mass. And if we look closer, we can see that jadarite is associated, forms together with chlorite and with secondary albite. So we have a late stage process of lithium and sodium metasomatism. And the presence of chlorite is going to bracket our temperature to relatively higher values, ideally, if compared to nodular jadarite. So we have at least a couple of generations of jadarite. So what is the timing relationship? We can nicely see in this automated SCM map that nodular jadarite is coated by ghost jadarite. So nodular jadarite is definitely coming earlier into the story. Now, let's address perhaps what is the most interesting part of the story, how jadarite actually formed. And we're going to do that by addressing some pretty basic geological questions and by doing some pretty basic geological observations. And one of the most basic geological observations we do in our work is trying to figure out timing, what comes first into a system. So we have lithium smectite and jadarite. Which comes first? So if we look at drill ports, we can see that lithium clay-rich pods are overprinted by jadarite and dolomite. So jadarite arguably forms a bit later if compared to lithium smectite. And this has been confirmed also by more sophisticated analysis like SCM mapping, TEM, showing that the dolomite associated with jadarite replaces lithium smectite. The second observation is that volcano sedimentary deposits, by definition, are associated with highly fractionated volcanics. And Jadar is no different. It's pretty close to Mount Sur, a highly fractionated granite. On top of that, within the basin, we have felsic tuffs. So the question to be addressed is, where is primary quartz? And I can tell you with a decent level of confidence that at least in the mineralized units, there is very little primary quartz. Okay? Why is that? So, although there's no primary quartz, in association with jadarite, we have quite a lot of poorly crystalline silica compounds. We can see that jadarite nodules are ringed by silica. And if we look at the mineralized sequence in veins, we have an early jadarite generation. Then we have silesite in purple, silesite, which is a sodium borosilicate without lithium. And then later on, we have secondary silica. So if we want to simplify this pathway, we have a fluid pretty much enriched in silicon, boron, sodium, lithium, and this fluid starts precipitating jadarite. So jadarite takes all the lithium available, but arguably the fluid has more silica, boron, and sodium than lithium. So we have an excess of this element, leading to the formation of silesite and secondary silica. So, although there's no primary quartz, silica saturation is required to form jadarite. So what is the source of silica? I like to show this image. So this is an SCM image of the intrabasinal tuffs within the basin. What we see is a fine-grained secondary matrix with some voids. This kind of texture is pretty typical of high sulfidation systems on top of porphyry coppers, where we have low pH fluids leaching out alkalines and concentrating silica in the form of vaggy silica. But in this case, the residuum species, the ground mass, is not silica, are secondary K feldspar. So we still have a pH aggressive process, but it's not acidic, it's hyperalkaline, able to remobilize silica from the ground mass and to enrich alkalines such as potassium in the form of secondary K feldspar. So the answer is, in the Jada deposit, silica is highly mobile. So based on this observation, we can put forward a working hypothesis we want to test. The following: jadarite formed a pretty high pH with values exceeding those of the field of metastability of quartz and silica compounds, so pretty high pH. It required high silica activity, and the silica has been provided by the solution of volcanoclastic units. And jadarite formed through silica gels derived from this dissolution process. So this is the working hypothesis, and in collaboration with the University of Glasgow, we tested this hypothesis through mineral synthesis experiments. So what the Glasgow unit did is, using high temperature vessel, and they put colloidal silica as a silica source and also to mimic the presence of a silica gel. And this silica has been doped with sodium hydroxide and borax to increase pH and to provide sodium and boron to the system. And they also use lithium nitrate as a lithium source. So these, ingredients were left cook for a couple of days, 3 days actually. And we measured the mineralogy of what is produced from these experiments, okay? By doing XRD, we made sure that what was produced was actually jadarite. So we can see a nice match between the synthetic material and the X-ray signature of natural and theoretical jadarite. But we got pretty, excited about it. So we also measured these synthetic products at SEM to see if we could tell the paragenetic pathway. And this is what we got. So this is an SEM map of the synthetic product, where we can see early jadarite in red, then we have later cellulosite in purple, and then we have silica in blue as an excess. And this kind of pathway mirrors perfectly what we see in the natural samples as this mineralized vein, okay? That was a nice day in the lab, by the way. So let's take a step back and see what we got so far. So paragenesis, experiments, and so on are telling us that the ectorite, lithium smectite, and jadarite assemblages are not in equilibrium. So we started wondering if the ectorite and jadarite forming fluids are even the same. And to test potential differences, we did quite a lot of isotopes. Okay, so we did stable isotopes, which allows to calculate temperature and fluid composition and then define the source. But there are some challenges, because if we look at the fractionation equations, these equations have two unknown variables: the composition of the mother fluid and the temperature. So in terms of mathematics, these accommodates infinite solution. So a way to turn this around is using two equations at once. So using mineral pairs under equilibrium. But equilibrium conditions are assumptions that must be supported by mineralogy and petrography. And if this assumption is not supported, we are gonna go through terrible pitfalls, okay? So this is the fractionation equation of jadarite in red. What if we plot the fractionation equation for oxygen isotopes of dolomite? We can see that at some point they meet each other. So maybe they actually formed under equilibrium. So we have some junction points. But again, we need to support our assumption of equilibrium. So we went back to our samples, and what we saw is that the jadarite nucleation led to the soft sediment deformation of the surrounding dolomite sediments. So they arguably formed either at once or one shortly after the other. So from the same type of fluid. So the equilibrium condition is kind of supported. So based on this, what we got is that jadarite and dolomite formed between 65 to 90 degrees from a fluid having a delta O18 composition up to 5 per mil. So these are pretty isotopically heavy signatures that nowadays are mostly observed, for example, in modern alkaline lakes developed in volcanic terrains where lake water can have pH as high as 10, 11, and so on. What about smectite? So our hypothesis is that smectite is not in equilibrium. So if we plot the curve calculated for smectite, we can see that this curve doesn't meet dolomite and jadarite. And this is also supported by petrography because we see that dolomite replaces lithium smectite. So what we did is using the temperature defined before, and what we obtained is that the ectorite, this lithium smectite forming fluid, is much lighter in terms of isotopes, with ratios as low as minus 12 per mil delta O18. This is meteoric water. So jadarite is somehow associated with isotopically heavy brine, while ectorite, meteoric water. So this opens up to another question. What is the geological trigger to shift the fluid reservoir? So we did isotopes on dolomite, and we can see that the main feature to observe is a shift in the delta O18. And this kind of shift towards increasing delta O18 values is typical of shallow system experiencing seasonal evaporation. We have evidence of evaporation also by looking at rocks, because if we see drill cores in the other basin, we can see that jadarite nodules locally form these strange-looking veins called enterolites. Enterolites are observed in modern evaporite systems, and they generally form during periods of high aridity when we have the lowering of the water table within the sedimentary package and the onset of capillary flow leading to the coalescing of nodules. In modern evaporite systems, these are mostly gypsum. In the other basin is jadarite. So we have different fluids with different pH conditions, and different pH conditions obviously control what kind of assemblage we form on a basin scale. So we can argue that the facies mostly influenced by meteoric water recharge in a lake are the marginal facies. In fact, in the marginal facies of these kind of systems, we start crystallizing ectorite and so on, because these are stable under near neutral pH, whereas highly fractionated and high pH brines generally form so-called brine tube systems in the intrabasinal facies, where we have higher pH assemblages like zeolites, jadarite in the other case, sodium borates, and so on. And this is somehow confirmed by the geochemistry of the other basin, where if we cast boron against the sodium-calcium ratio, we can see a correlation mostly in the intrabasinal facies due to the presence of jadarite and other sodium borates. While if we cast magnesium against the lithium and boron ratio, we see an increasing lithium and boron ratio in the marginal facies due to the presence of magnesium-lithium clays. So we have mostly described what happens in the other basin during active lacustrine sedimentation. But the history of this study area is pretty complex, and we have a stage of marine transgression and subsidence of the basin. And this kind of late stage might have played a role in remobilizing lithium. And we have evidence for this kind of process because we can see that locally, jadarite nodules are not quite happy. They show dissolution features associated with secondary lithium and boron species like lithophosphate and sassolite. Now, sassolite is really interesting because sassolite is a boron hydroxide that is typical in fluid inclusion of grisens. Grisens, we all know that evolve under pretty low pH conditions. So we have evidence that at some point the alkalinity in the other basin has been buffered and has been also inverted to be able to precipitate boron hydroxide. So what is the geological process? What is the geological trigger of this pH inversion? We started looking at redox-sensitive proxies in the basin, and these are some geochemical logs of uranium and moly, and we can see some significant anomalies associated with the mineralizing units. We also did quite a lot of laser ablation to make sure that what we saw was not only controlled by the distribution of detrital minerals. And we can see in these two maps that obviously the detrital minerals can control a little bit of moly, for example, these are sulfide, but we also see high concentration in the matrix associated with organics, because we are still dealing with the black shales formed into a lacustrine system. Why am I bringing up organics? Because the other basin has been buried through marine transgression and also reached the oil generation window. This means that it's a baked system in terms of temperature. And as soon as we start baking organic matter, what we have is the transformation of organic matter. And specifically, we start breaking down primary organics made of aliphatic compounds to form secondary organics like bitumen enriched in aromatic compounds. And the presence of aromatic compounds has been confirmed by spatially resolved Fourier transform infrared. Now, the presence of aromatic compounds is interesting because generally they form, and as soon as they form, they start releasing organic acids in the system. So it is very likely that the thermal baking transforming organics was the main trigger for the acidification of the system and therefore for the local dissolution of the adorite to form secondary lithium and boron species. As a last point, relationship with magmatism. Really important because this is our source of metals and also provides heat. Heat is important because its energy to the system increases the kinetics of reaction. Okay, as I mentioned before, we have two stages of magmatism: Oligocene, pre-mineralization; Miocene, syn-mineralization. If we look at the petrology of these rocks, we can see that the pre-mineralization granites are mostly metaluminous, so igneous granites, very low potential for lithium fertility, while the Miocene syn-mineralization granites show an increase of the aluminum saturation index. And the increase of the aluminum saturation index indicates that these are crustal granites deriving from the partial melting of metasediments, so higher potential to form lithium-bearing granites. So this shift of serial affinity is telling us that we change the region within the crust where we melt the source rock. And the shift of source rock is obviously supported also by trace elements, because we can see that the pre-mineralizing granites have very little rubidium, so they fall within the clay-poor sources like methamphibolite in the lower crust, while the Miocene syn-mineralization granites show rubidium anomaly, so clay-rich sources like metasediments, metagravici, and so on. Okay, so Mount Sir, those granites arguably have a role in providing lithium to the system, but we need to face a little problem. And the problem is that these granites have really low lithium. They have anomalous concentrations, but they are still not higher than 100 ppm lithium, a couple of order of magnitude below what we see in the other base. So we have a misfit of data we need to reconcile. And we have a couple of hypotheses. Hypothesis number one, these granites has been uplifted. Lithium is very mobile, so all the lithium contained has been leached out. A little bit simple. Hypothesis number two, a little bit better, is that lithium show a high partitioning in the vapor phase. So maybe left the granitic rock mass either during exsolution of fluids or maybe during eruption, okay? And we have a series of evidence as a support of hypothesis number two. Evidence number one is geochemistry. So the Mount Sir granites, although have relatively little lithium, show anomaly of rubidium and cesium, which behave like lithium but have a lower partition coefficient in the magmatic vapor phase. So maybe they represent what is left from this process. Hypothesis number 2 is the modeling of strontium isotopes. This modeling has been made of separates from the mineralizing units from the other deposit and compared with the Mountain granites. And we can see that the isotopic composition can be explained by this end member, which are the Miocene zinc mineralization granite. Hypothesis number 3, the last one, evidence number 3, sorry, is that if we look in the tuffs, the very early stages of jadarite and hectorite formation involved in situ replacement of vesiculated material with bubble morphology. So this is what is left from the in situ replacement of volcanic glass shards. Right? We still have a couple of things we don't know yet. Okay. First point is that we don't know quite well if the intrabasinal tuffs in the other basin are the exclusive expression of Munzer or they were sourced from another area. We don't know if the initial metals endowment in Munzer can actually explain the volumes of metals we see in the other basin in terms of mass balance volume, mass balance problem, okay? And we don't know if these granites were lithium fertile. We don't know the mineralogical residency of lithium in these granites. Okay, so to conclude, the Jada deposit has a pretty complex evolution. We have several stages to it. Stage number 1, obviously, we have this continental basin experiencing deposition of highly fractionated volcanic glass, and this glass, during the very early stages of alteration, was influenced by circulation of intermediate pH meteoric water. So we break down glass and we form lithium smectite. But during seasons of high evaporation, we have the increase of pH of lake water. So we break down lithium smectite through dolomitization, and the breakdown of smectite is able to remobilize lithium and silica and to produce silica gels that are going to migrate through density in the intrabasinal fascies, where they are going to produce extensive zeolitization associated with the jadarite formation. So that's it. Thank you very much. I'm happy to take any question.
Thanks, Francesco. Questions? Wanda? Is there any question from online? Please just open the microphone.
Yeah, you can unmute yourself if you want to ask some question. Thanks.
I have some comments. First of all, can you hear me?
Yep.
Okay, first of all, many thanks to Francesco for this very interesting presentation. A couple of curiosity. You mentioned several times zeolites. Zeolites, you said sodium zeolites, and you mentioned analcime natrolite. Do you have any hint if there is one type or another type? Because
both of them.
Mm-hmm. And you, how do you discriminate between the two of them?
X-ray diffraction.
Okay. And then you mentioned also calcium zeolite. It would be nice to specify which type of zeolite, because you did a heck of a job on other minerals, but zeolites could have been investigated more correctly.
Yeah, definitely. So calcium zeolites, calcium sodium zeolites are present in volcano sedimentary deposits, but not in Jadar specifically. I have observed calcium-bearing zeolites mostly in McDermott, eulandite, and clinoptilolite.
Yes. Is it possible? Because you know that the closed lake system, it's one of the genetical model proposal for the genesis of zeolite. So I found out
Yeah,
a lot of similarities between
definitely,
the
definitely.
that you said to us about the formation of these different minerals. And
Yeah,
then
yeah.
just a quick comment. You mentioned during your presentation that smectite are not in equilibrium, right?
Yeah.
I have to tell you something. Smectite are never in equilibrium.
Yeah, that's a good point.
They used to evolve in maybe not in geological times. Okay, so once again, thank you, Francesco, and keep up the good work.
Cheers.
Other questions?
One question online. If you estimate which is the lithium. So Alessandro, estimating the lithium concentration of volcanoclastic rocks in Jada is pretty complicated because those rocks are completely altered. Okay, so what you see in terms of lithium concentration in volcanoclastics is not a primary endowment, unfortunately. Okay, so in the literature, we have some lithium data of igneous rocks from the nearby Mount Sir complex, as I showed in the presentation. But when it comes to intrabasinal tuffs, those numbers, they are not representative of primary lithium endowment.
I also have a question. Hi, Francesco. Hi.
Hello, Francesco. How are you?
It's Francesco, is your namesake. Excellent job. Thanks for the presentation. And I love the synthetic experiment. You know, it was very interesting, I think. And you left everything for 3 days, right? I was wondering if you did it also a
Well, you know,
different.
I didn't do the experimental stuff myself. That was a
Yes,
collaboration we had with a PhD student based at the University of Glasgow. So that
yes.
she published the work, so I can point you out to the
Yeah, yeah,
publication. But
yeah. I would
yeah,
read it, very, very interesting.
yeah,
You know, I
yeah,
was
yeah.
wondering, so the 3 days was to simulate, let's say, you said 3 days, no, sorry, not 3 months, no, so,
If I
no,
no, it's 3 days because that
three
was an
days.
high temperature vessel to
Yeah.
to increase the kinetics.
Yeah, no, I was wondering if changing the temporal resolution, if also the XRD would give like a different kind of ratios proportions, or is just the final. Anyway, it was, but you didn't do that. But I mean, I would read it. It was very interesting. Thanks.
Cheers.
Questions? Any other question?
From the audience in presence.
In presence? Just
Okay.
so thank you very much.
Thank you.
Thank you very much all for being here. Thank you again, Francesco, for giving this very pretty talk. Thank you.
Cheers.
Cheers.